We have to give proper credit where credit is due, and the fact is that we all wouldn't be here giving this nice presentation today if it weren't for one of our key customers, Syracuse University and their partner IBM Corporation, for moving forward with a green data center concept design in 2009 that GEM Energy and the Rudolph Libby companies were lucky enough to be a big part of. And we have several folks from Syracuse University in the audience today. And you know, Dr. Khalifa is one of our presenters who's going to talk about a modeling system that they've developed at Syracuse University to assist customers in modeling what a CHP system or a combined heat and power system can do for their facilities. So not only are they a good customer of ours, but they're trying to get the word out and try to help customers put this technology in their facilities. So I'd like to introduce Dr. Khalifa. He's an NY Star Distinguished Professor of Mechanical and Aerospace Engineering at Syracuse University. His career spans 4 decades of academic and industrial experience in teaching, research, technology and product development, and R&D planning and execution. He joined Syracuse University in 2001 after a 23-year career as a researcher, manager, and R&D director at United Technologies Corporation, where he was responsible for the development of numerous environmental control and energy conversion technologies and products, including vapor compressors, CCHP systems, geothermal and space power systems, and advanced refrigeration and IEQ systems. His current research is focused on transport processes in and the optimization of environmental control and energy conversion systems, particularly those applicable to buildings and high-density data centers. Dr. Khalifa holds a PhD in thermo and fluid dynamics from Brown University. He's a fellow of ASME and ASHRAE, senior member of AIAA, and a member of APS and Sigma Chi. I'd like you all to give a warm welcome to Dr. Khalifa.
Thank you very much, Sam, and thanks for inviting us. The 2 presentations that preceded me were excellent presentations. Dr. Schmidt introduced the concept to you, so mine is a follow-up on Roger. Roger has been my partner for the past 3 or 4 years in the development and the research related to high-density data centers. Okay. These are the topics I'm going to be talking about. Okay. Why cogeneration systems for data centers? Some people call them trigen. I'm going to just use the word cogen for simplicity. Give you an idea about the simple configuration of cogeneration systems. Okay, then I'll go through a multi-city assessment of cogeneration systems compared with conventional systems for powering and cooling data centers at 11 cities spanning the entire range in the US, climates, energy prices in the US. And then I'll focus a little bit on a special case of a data center for a healthcare facility in northern Pennsylvania. And then I will show some slides about the SU Green Data Center. I should call it the SU IBM Green Data Center, okay, which was the first in the world, as far as I know, to use cogeneration for powering and cooling a data center. Then, before I show you some experimental results, measurements that we have been taking continuously, every 2 minutes we're taking measurements everywhere in our data center and its infrastructure. Before I show you this, I'd like to introduce metrics that are suitable for assessing the performance of cogeneration powered and cooled data centers. The PUE by itself is not sufficient to express the performance potential of cogeneration systems, and we had to introduce new metrics that will allow us to assess the overall performance of these data centers. You have seen this picture, okay? Dr. Schmidt showed you this picture. It's a little bit different, okay? I think I end up with 33 units. He ended up with 30 units, so he stole 3 units somewhere, okay? Okay. No, but 30% is a good number, okay? But I'm not introducing this to repeat what Roger mentioned, but just to point to the fact that because the central power plant that generates the electricity that feeds a data center could be 50 or 100 miles away, that extensive amount, there is a very large amount of waste heat, okay, from the power plant. We say the power plant is 35% efficient, which means 65% of the fuel energy in the power plant is dissipated, is lost. I cannot transport it over a long distance of 50 or 100 miles, okay? However, if I were to put the power generation system on site, then I'll have the opportunity to use the waste heat. And this is one of the advantages of using cogeneration or on-site power generation, is now it gives me the opportunity to utilize that waste heat to provide free cooling to the data center, as we'll see in this example. So why cogeneration for data centers? With the on-site generation of power, the waste heat from the power plant could be used for useful things, such as producing cooling in an absorption chiller or producing heating, not because we need to heat the data center, they have enough heat by themselves, but to heat an adjacent building. Okay, the University of Toledo and Syracuse University before this are very good examples, because when you embed a data center within a campus, you have opportunities for using the waste heat to a much larger extent compared with just using it to feed the data center. So campuses are excellent opportunities for using the cogeneration system, or any data center that's embedded within a larger building or a larger complex of buildings, not the standalone ones that are isolated. Here's one other advantage that is not obvious. Okay? One of the problems in the determining the efficiency and economics of cogeneration systems in general, if you're using a cogeneration system for an office building, is the issue is the demand for electricity and demand for thermal energy, whether it's cooling or heating, in commercial buildings do not coincide. I mean, there are times in the year where you need cooling, other times where you need heating, and times where you need neither. So the issue of utilizing that waste heat depends a lot on the correlation between the thermal loads of the building and the electric loads. Data centers are different. There is a very strong correlation between the demand for electricity and the demand for cooling. In essence, you feed them electricity, as Roger showed, and you turn around and having to remove that heat. So that strong correlation ensures a higher level of utilization of the waste heat compared, say, with a cogeneration system used in an office building. The third advantage of using cogeneration in data centers is computers are inherently DC devices. They're not AC devices. So what do we do in a data center? We take AC from the grid, okay? We rectify it, we feed the batteries and the UPS, then we invert it again, then distribute it, then feed it into the computer where it's rectified again, okay, into a high voltage DC, then step down to a low voltage DC. And that cascade of conversions from AC to DC to AC to DC, like a data center of, say, 5 or 6 years ago, will lose 25–30% of the electricity in that process. The newer ones are much more efficient, but there have been studies showing that it is possible, if you distribute DC directly in a data center, you can save another 10% on top of the savings that we're going to show as a result of the use of cogeneration system. Now, why is this important in a cogeneration system? If I'm generating power on site, there's nothing that says this power has to be AC. Yeah. In fact, if you look at the micro-turbine, the Capstone turbine, okay, the turbine drives a high-frequency alternator that is immediately rectified. So you have a bus inside the turbine that's DC. So if you were to tap the DC directly from this, I'm not talking about today, but in the future, okay, then I can actually avoid having these multiple conversions and I can gain the efficiency. So that's another advantage you get by having the power generated on site. Obviously, there are other types of power sources that are not commercially widely available yet, such as fuel cells, which are natively DC. They just generate DC. Okay. Then the other thing is when you have these cogeneration systems on site, you can build in redundancies in the system itself that will obviate the need for having backup diesel generators and things of that sort. Okay. In our case, okay, the worst that can happen to us, aside from equipment failure, but this is handled through redundancy, the worst is an interruption. It's not an interruption of electricity, it's an interruption of natural gas. But if you have an interruption of natural gas, you can always have a tank containing a substitute for natural gas. In our case, it's propane that can actually run on this on several days until they fix the gas line. So you have built-in redundancies that can actually reduce the capital cost of the equipment, okay, because of the configuration of the system. Just a very simple diagram of what a cogeneration system looks like. Okay, so we have these micro-turbines. Okay, you get the redundancy by having one spare. Okay, Energy computed the reliability of the system based on the inherent reliability of these turbines, and we figured that by having one extra turbine, we can actually meet a very high reliability of the entire system. You take the electricity from the turbine and goes to feed the data center. Then you take the waste heat into a cooling system called an absorption. It's a thermochemical device that runs on heat and generates cooling. Okay? Then that cooling, some of it may go to the data center, as you see at the bottom there. So some of it provides the cooling for the data center, so you're providing the cooling for the data center for free in this case. If you remember what Roger said is that cooling, which includes chillers and air movers, consumes nearly 33% of the total power consumption of a data center. Okay? And if you have excess heat and you happen to have an adjacent building, you can take the exhaust, use it for heating water, and you can send that water to the adjacent building to heat it in the winter, or you can take any excess cooling as chilled water and send it to the building to cool it in the summer. Okay? So you have a very high utilization of the potential waste streams, the various waste streams from a cogeneration system like this. If you don't have an adjacent building, then the only thermal load you'll have will be the cooling requirement required for the data center. So one of the issues with cogeneration systems is you cannot just compute their performance and the economics based on design points, because there's always the issue of how much of the waste heat can be used. And how much of the waste heat can be used depends a lot on the weather, which is a time-dependent situation. Depends on the nature of the load in the building. Like if it's a commercial building, an office building, there are occupancy times where the lights are on and the computers are on and the temperature in the summer has to be maintained at a comfortable level. So there is a time-dependent nature of the consumption of the thermal energy that I cannot capture short of doing an hour-by-hour simulation that takes into account the variations of the weather, like the changes in the ambient temperature, ambient humidity, the loads in the building from the solar energy or from resulting from occupancy. All of these things are time-dependent. And because the demand will be time-dependent, then the equipment will not always perform at its peak efficiency or design efficiency. So you have to have models that account for the off-design performance of the equipment as the load on the equipment changes hour by hour, either because of the weather or because of the nature of the load. So we have developed a suite of tools that will allow us to do this for data centers of different configurations, conventional, ones with cogenerations, ones with water economizers, with air economizers. A very wide variety of equipment are included in that suite of tools that we can use for analyzing data centers almost anywhere. Okay. So the cases I'm going to show you is a study of cogeneration systems applied to a nominal 1 megawatt electric IT. Okay. 1 megawatt IT data center, 1,000 kilowatt IT data center. Okay. I'll show you the definition of that in the next slide. We analyze it in a number of operating modes. In cogeneration, sometimes you size them to match the thermal load. So for a data center, the thermal load is a cooling load, so we call it cooling matching. So you size the equipment so that its cooling output is matched to the data center. Okay. Or you can size it so that its power output is matched to the data center. Okay. And when you size it this way or that way, it depends also whether you have a building. So the first case is a case of cooling matching with no adjacent building. NAB means no adjacent building. The only consumer of thermal energy will be the cooling for the data center. The next one is also cooling matching with either a small adjacent building, okay, or a large adjacent building. A large adjacent building will size so that in the peak load, whether it's a summer load or it's a winter load, okay, it can use all the output of the data center at that particular hour in which the load is at its maximum. Okay. So if you do cooling matching, obviously you're not going to be able to provide the entire requirements, electric requirements of the data center. So that data center has to be connected to the grid, and you have to compensate for the fact that we're not generating enough power by importing power from the grid. So it's going to be some sort of a hybrid combination. Part of the electricity is coming from the grid, and part of the electricity is generated by the cogeneration system. Okay. If it's power matched, okay, then you can imagine that at some time when people are comfortable, okay, with that technology, that you could be totally isolated from the grid. Okay. So that describes the power matching, and I said we do both power matching and cooling matching with either a small adjacent building that cannot use all the output, thermal output of the system, or with a large building. So we're going to do all the comparison, okay, to a conventional data center that looks like this. It has 1,000 kilowatts of IT load. It is cooled by a stream of chilled water at 15, okay, I'm sorry, has a 15 degrees temperature rise across the servers. Okay, it's an open aisle, okay, with no economizer. Okay, the water, chilled water comes in at 7 degrees Celsius, okay, which is typical if you're using a chiller. Okay. The cross applies air at 14 degrees Celsius. Okay, the ratio of the flow coming out of the tower to the flow that goes through the servers is 90%. Okay, there's 25% flow leakage outside either through the cutouts or through the various leakage path on the floor. And that data center will be very much like the one that Roger talked about that has a PUE. That's the combination, that's the sum of the infrastructure power and the IT power divided by the IT power equals 2. That's sort of old technology. I think the newer ones, there was a recent study of 1,100 data centers that showed that the number now is more, if you look at all of those, was about 1.8, 1.85, I think. Yeah. So that's our base, but it's not the same thing because if we put it in Los Angeles, it's not going to perform the same way as it will if we put it in New York City. So when we do this analysis, we do this hour-by-hour analysis, both for the conventional data center and for the cogeneration data center. Okay, so that's the first slide of comparing these cities. You can see New York City, Los Angeles, Atlanta, Washington, D.C., Denver, Boston, Chicago, Philadelphia, Dallas, and St. Louis. Okay, each one of those has a different energy cost, both natural gas, the fuel for the micro-turbines, and for electricity, and they have different climates. Okay? So what you see here is the present value of the energy cost savings. The cogeneration system will save some money in many of these cities, and the secret for the high savings will be a situation in which the price of electricity is high and the price of gas is lower. Okay? So each one of those cities has its own structure in the rates for gas and electricity, and these are completely included in this comparison here. And the various lines you see in this arachnoid diagram are the various configurations I mentioned before: cooling matching, power matching, small building, big building, no building, and so forth. Okay? So what you can see is a place like New York City, where electricity is very expensive, sort of like 21 cents a kilowatt hour or 22 cents a kilowatt hour. Gas is also expensive, but the spread between gas and electricity is so large that these systems show a huge advantage. It's expressed here as a present value of the energy cost savings over 20 years at some discount rate. Okay? So you look at cities like New York City, Los Angeles, Atlanta, Washington, D.C., all of them, then you come to places like Dallas and St. Louis, and you find that you end up with negative present values, okay, which means you're not saving, and there are reasons for this. St. Louis, okay, and Dallas, they have very cheap electricity, okay, and the gas prices are not commensurately cheaper. Even if both of them are cheaper, it's the spread, it's actual spread between them, it's not the ratio of the two that matters in this case. So clearly, okay, you cannot make a case for using one of these cogeneration systems in a data center in a place like St. Louis, where most of the electricity generated from coal and it's relatively inexpensive, okay? And the same thing with Dallas, okay? But almost everywhere else, looks like we can make a case. But this is just the present value of the energy savings. Obviously, you have to pay extra money for installing the cogeneration equipment. The next slide will give you the net present value, which takes into account the cost of the cogeneration system based on the ReliaFlex, okay, estimates. The trend is again similar. This is now the net present value, which includes the capital cost of the equipment, includes also the operation and maintenance costs, including replacements of equipment at periodic time. Like for a conventional system, you have to change the UPS every so often. This has all estimates of the maintenance. In the case of the cogeneration system, I think one of the options available from GEM is to buy a maintenance contract. It's a flat fee you pay, okay, and they take care of the maintenance and replacement. I believe the turbines require some sort of a rebuild every 7 years or so. Okay, that's all included in this. And you see again the trend is the same. Okay, cities like New York and Los Angeles and Atlanta, all of those, if the net present value is greater than 0, then you are making more than your cost of money. Okay. So all of these things, except again, you get into Dallas and you get into St. Louis and you find this notch there, which means they're still not very attractive as prospects for using cogeneration systems if these data centers are there. You can, instead of a net present value, you can do it as a rate of return. Okay, so this is just a reflection of the rate of return. And again, the trends are there, although you look at the rate of return is reversed between the cooling matching and the power matching. The net present value is a much more robust criterion for judging these things than the IRR. Many of these cogeneration systems, and they're in their infancy, okay? So their price is a bit more expensive, but they deserve encouragement. Okay, they actually receive encouragements from the various states. Many states have incentives for those. Okay, at Syracuse University, you obtained a $2 million incentive from NYSERDA, the New York State Energy Research and Development Authority. And I believe most of the markets in which you sell have some sort of an incentive. Yes. It varies, but they have this. So we just said, what if you get a $2 million incentive? And the results, of course, improve, okay, with the addition of the incentive. But still, this notch about Dallas and St. Louis remains. This is the IRR equivalent to that one. Now, the picture here looks a lot different. What we're looking at is, would a cogeneration system reduce the greenhouse gas emissions? And the answer is, it looks like it does, but the thing that you'll probably be surprised about is, why do I save a lot more in a place like St. Louis, which proved to be uneconomical? And the reason is, we're always comparing with the electricity generation mix from fossil fuels in the various states or various locations. In St. Louis, almost all their electricity is generated from coal. In New York and California, okay, most of the electricity is not generated from fossil fuels, and whatever electricity generated from fossil fuels is from natural gas. Okay? But they have a fairly large percentage of their electricity from either nuclear or hydro, or small amounts from other types of renewables. So when you're comparing with a location in which the electricity is relatively benign when it comes to emissions of greenhouse gases, okay, you'll not see as big an advantage of the cogeneration system as when you compare with a place like St. Louis, where they produce huge amounts of greenhouse gases, CO2, because the major source of electricity is coal. The case study I'm going to show is a location is northern Pennsylvania. It's a 200 kilowatt IT, which will end up being roughly 300 kilowatts total. Okay? For the initial capability, the intention of this particular location was to grow. Okay? You want to use something that's modular. You start with this, and they have anticipation that they're going to be needing more capacity. You just add more modules in that case. Okay? It was to achieve a tier 3. It's a health facility complex. So for them, that's a mission critical facility also, where the reliability is very important. So they wanted tier 3 reliability. So the systems were configured, both the cogeneration system and the conventional system, to satisfy the requirements for a tier 3 reliability. And the comparison was done very much as I did before. Now, the local energy costs, as they existed at the time we did the study, were as shown in that scenario 1. Okay? Then there was another scenario we looked at, because in Pennsylvania in particular, they're doing lots of hydrofracking, and they're obtaining relatively cheap natural gas. And if you go look at the price of natural gas at the Henry Hub, okay, you're going to find that you can buy 1 million BTUs of natural gas for something like $2.80 or something like this. Okay? If you add transportation and distribution expenses, we figured that there will be more like 44 cents a therm, or $4.4 a million BTU. So we actually did the analysis for all 3 scenarios. Okay? But the one I'm going to show you is that middle scenario, which is sort of an average between the two. Okay? So I'm going to show you results for that middle scenario, but we did the analysis for all the scenarios. And in every case, we included the real escalation rates of electricity and gas in that state, according to the Department of Energy. So here are the 2 scenarios. The gas scenario 1, which is the current prices of gas and electricity, and gas scenario 3, which is the other end of it, which is the same price of electricity, but prices of gas reflecting the cheaper gas that you can get nowadays. Okay? And the savings are fairly significant, especially with respect to, these are annual savings reflected as year 1, because we add an escalation factor for these things over the life of the equipment. Okay? So you see significantly more savings if we use the scenario 3. With respect to the incremental rate of return, the rate of return on the incremental investment to the cogeneration system, it depends a lot on how much incentive you can get. But if you were to get something like that 2 million incentive, then you're talking about an internal rate of return of about 60%. That's fantastic okay, if you were to get this. If you don't get anything, probably it's not going to be very attractive given the cheap electricity in that particular location. This is a comparison of the CO2 emissions and the water consumption also, okay? So the conventional system is the red bars, and the green bars represent the cogeneration system. Not only will you save, okay, reduce the emissions of CO2 when you use cogeneration, but you can also cut the consumption of water quite substantially if you use the cogeneration system. Now I'll just give you a quick tour. I think some of the slides Roger has shown also before, so I'm not going to dwell too long on these slides, but this is sort of a high-level view of our green data center at Syracuse University. It's powered and cooled by the on-site cooling, combined cooling, heating, and power systems. There are 12 Capstone C65 turbines in 2 strings. There are 2 identical strings like A and B, will look like mirror images. Okay? Each one of them has 6. Okay? Our data center is still growing. We are moving assets from scattered data centers around the campus into that data center. So right now we're running only at about 250 kilowatts IT, but we designed it so that it can support 500 kilowatts IT. Yeah. There are 2 waste heat activated double effect 2-stage absorption chillers, okay, 1 for each string. Each one of them is about 150 tons of cooling. Okay, the power supply is a dual mode. Okay, they have these hybrid turbines. Maybe Sam will talk about the architecture of these turbines later. Okay, just to explain some of these things, I need to premise this by saying our CIO was a very open-minded guy who was actually willing to use our production data center for trying something that's brand new like this that has never been tried before. Okay. As Roger mentioned, the industry tends to be very conservative, and anything that's different they're not going to use. Okay. But we were lucky to have a CIO who was open-minded and willing to try something new, but we had to pay, there was a quid pro quo. Okay. Quid pro quo is say, if you're going to use this equipment on my data center, I want belts and suspenders and duct tape and all sorts of things. So that many of the equipment that we put in the data center, I do not envision these to be present in a future data center that has been built after the technology has been proved. We did this for the peace of mind of our CIO. Okay. So we have the grid connected or grid independent operation. We can do either. Okay. But grid connected, because it doesn't know, this is new equipment, I don't know whether it's going to work, or it's going to work reliably or not. Okay, we have battery backup. There's no conventional UPS. The turbines provide that function, and we have a room full of batteries. Some of the weight of that batteries would have been residing in the bottom of the turbine anyhow. So we have 44 tons of batteries that can run that data center at full power, at 500 kilowatts for 22 minutes. Yeah. It has the propane fuel emergency tank that we can run on a couple of days on the propane tank in case somebody punctured the gas line. That will be our biggest risk. We are not vulnerable to an electricity interruption, okay, but I think all of us know how often did you have an interruption in the supply of gas compared with electricity. I'm sure most of us have seen more interruptions of electricity compared with gas. Okay. And even if we have an interruption in gas, we have these propane tanks that we can run on until they fix they can be replenished. They can bring trucks and replenish them until they fix the pipeline. Extensive use of water-cooled racks. Almost every rack we have in our data center is water-cooled on the rack level. Roger showed you pictures where you're doing water cooling on the module level, inside the boxes, inside the computers themselves. Okay, this is water cooling on the rack level. There is a couple of advantages to this. The closer you bring the cooling to the source of heat, the more efficient your system will be. Obviously, if you bring the cooling directly to the chip, that will be the most efficient way of cooling it. This is why he was able to raise the temperature. Okay? But next to this is bring the cooling to the rack. So each one of these racks has a heat exchanger. It looks like a car radiator, okay, that's cooled with water above the dew point. It's about 65 degrees Fahrenheit. That is about 17 degrees Celsius, compared with the 7 degrees that you have to feed into a CRA or a CRA unit, okay? So you can actually operate your chillers at an elevated chilled water temperature if all your data center is cooled with these heat exchangers. The other thing is if I put the cooling immediately in on the rack, then I don't have to move all that air. Now, Roger did not break up the thing that you call cooling 33%. Unlike, say, a house or a commercial building where the amount of energy used for moving the air may not be as very significant, in a data center, it's almost as much as a chiller, okay? So if you put the heat exchanger in the back of the rack, I don't have to move as much air, okay? So when you see the performance of our data center, the measurements I'm gonna show you, okay, the contributions to the improved performance of our data center comes from multiple sources. One of them, of course, is the fact that we're getting free cooling because of the absorption chillers on site. The other one is the fact that we have actually two large CRAs in the three large CRAs over there, but only one of them is sort of idling. Okay, like it's sort of a backup. We still have some equipment that is not cooled with these heat exchangers. We have 35 racks in the data center. Each and every one of them has some sort of either a rear door heat exchanger or a much bigger heat exchanger that resides on the side of the rack. You're going to see this in the pictures. The surplus cooling and heating and possibly power could be shipped to other buildings on campus to increase the utilization of the system. Okay? And our goal was actually to demonstrate a 50% reduction in the primary energy consumption, and we are close to actually achieving this level. You saw this picture. These are the 12 Capstone turbines. Roger showed this picture. Okay, the exhaust from those is collected and piped to the room next door. Okay, each 6 of the turbines are ganged together, and they feed one of these 2 absorption chillers. These are double effect, 2-stage absorption chillers. They have a thermal COP in excess of 1.3. In other words, for every unit of heat you put in, then you get 1.3 units of cooling. Okay. These are made by Thermax. The system we're going to see this afternoon is more of the package type. Okay. These are the exhaust-fired heat exchangers. These are the ones that can use for providing hot water to the adjacent building. We don't need this for the data center. There are 2 of them, again, 1 per side, and they can send, like in cases where you, in the winter, for example, I may not need all the cooling, so I can actually divert the exhaust into one of these heat exchangers and provide hot water to the adjacent building for heating. These are the heat exchangers. You can see one of these heat exchangers here, the rear door heat exchanger. In essence, in the back of the rack, you put a heat exchanger that looks like a car radiator. It does not have a fan. It relies on the fans and the servers to move the air through it. The pressure drop through it is very small, okay? And that one can remove in excess of 10 kilowatts of heat from a rack. Most racks are about that. It can actually do more than this. There's another type where you put the heat exchanger on the side, and that can remove 30, 35 kilowatts of heat, okay? And I don't have to feed them chilled water at 7 degrees Celsius as you do in a CRA, a computer room air conditioner. We feed them water at 65 degrees to prevent condensation. Okay, so it's above the dew point to prevent any condensation, and they work fine. Okay, with respect to the DC, you cannot go and order from the catalog DC computers. They have to be special ordered. Okay, can they be special ordered, Roger, or
you can order.
You can?
Sure.
You can order them now. So you can order, okay, this happened to be specially modified mainframe Z10, was specially modified for this application by IBM, okay, and it's running on DC. So not all of our data center is running on DC, but this particular computer is running on DC. I would expect we can run any computer on DC. We have the DC power distribution system in the data center that will allow us to run any computer on the DC when we replace these computers with DC computers or when they become more available. To describe the performance of these data centers, in essence, you need to compare them. Here's that thing is like that. This picture on the side is the cogeneration system, okay? Or I can have. I'm sorry. This is the grid case, okay? So you have the electric grid, okay? You take electricity from the grid. You either feed the IT loads and associated electric loads in the data center, or you feed the cooling equipment. I'm just representing it as a chiller. There are pumps, there are fans, there are all sorts of things, okay? Then there are other DC loads, data center loads, okay? I mean, there could be the blowers in the crowd, for example, okay? Lights, things of that sort. Then there's a chiller. Then you take the condenser heat from the chiller and throw it in the environment through a cooling tower. So this is the way a conventional data center is running. Okay, if you do any heat recovery, okay, remember what Roger said is one of the things that people are interested in is since these computers produce a lot of waste heat, is if you can use that waste heat, then you can improve the overall efficiency, energy utilization efficiency of the data center. Green Grid introduced a metric, okay, for accounting for this utilization of the waste heat. It's called energy reuse effectiveness, ERE, okay? So the PUE is the one defined over there. I'm defining it in terms of energy, not power, so that's integrated over some period of time. The IT is the energy used by the IT equipment. IS is the infrastructure, and that's the normal definition of the PUE. The ERE is somewhat different, is they look at any energy that's being exported. So if I were to take the waste heat from this data center, whether it has a cogeneration system or a conventional system, and send it to a greenhouse next door, then that amount Q exported, they subtract it from the numerator of what would have been the PUE, but they don't define it as PUE prime or PUE2. They define it as energy reuse effectiveness. So it's possible in this case to end up with EREs that are less than 1. Okay? But it does not mean that the PUE is less than 1. It just means that the ERE is less than 1. I hate this expression. Right? Yeah. You see, I'm a thermodynamicist. I teach thermodynamics. And it is sort of a sin to subtract heat from work. Okay? Okay, so we decided that we need to modify this to make it more rational. Okay? And the idea is, if I have heat recovery, I'm going to exporting this amount and goes to adjacent building. That would have displaced some gas or oil that you would have used for heating that building. So they take that and just subtract it from there. So here's the PUE, and here's the ERE defined by the green grid. It's expressed over there. Okay, the electricity is apples and the heat is oranges. You cannot add or subtract apples from oranges, or oranges from apples in this case, okay? So we have to make an adjustment. The thermodynamic worth of that amount of heat exported, or the economic worth of that heat exported, is not the same, okay? So even though in kilowatt hours they numerically have the same number, but their utility, I think the economists use a concept called utility. Their utility is completely different. Okay, so we had to define modifications of the ERE that take into account the difference in either the thermodynamic worth or the economic worth of that amount of heat exported. Now, Green Grid was not talking about cogeneration. They were talking about just using the heat directly from the computer to send it to a building next door or a greenhouse or something else. Okay? In our case, it's much more acute because we have a huge amount of heat that's available from the cogeneration system, and a large fraction of this is exported to the adjacent building. So we need to do the same thing. So it's the same expression I showed before, but I'm going to call it ERE prime. Okay? And the difference is there's a multiplier. So it's just simple multiplier of the amount of heat to make it economically or thermodynamically equivalent to the electricity. Okay? There are a number of ways of getting the value of this. If it's based on economics, I'm going to look at how much money will I have paid to obtain that amount QEX by burning fuel in a furnace, okay, compared with the price of electricity. So you can use the economic equivalence between gas and electricity to convert those two to the same thing. So I can actually use CR to be the economic equivalent in electricity terms of that amount of heat. Okay? It turns out in most places, if you look at the relative ratio of the relative cost of electricity and gas all over the country, the number on the average is about 0.35 in the same units. It's not like kilowatt hours per BTU, it's kilojoules per kilojoules or BTU per BTU. It varies from one place to another, but the average is about 0.35. Okay? If you do it thermodynamically, you can ask, okay, if I'm going to displace fuel, I could have burned the fuel in the turbine and generated additional electricity. So I have another conversion factor that's thermodynamically based, which is the conversion efficiency of fuel to electricity in the turbine or in an engine. Okay? And that ends up being about 0.3. Okay? So it turns out that you look at it this way or that way, either thermodynamically or economically, and the conversion factor is about 1/3. Okay? So you can simply modify, because sometimes when you have metrics like this, the industry will shy away from using it because it's too complex. Okay? So we made it very simple. Just take that amount of heat and divide it by 3. And that will actually fix the problem with the thermodynamic disparity between heat and electricity, and will fix also the economic disparity between the two. So just, if you want to do a better expression, just divide it by 3. We do better than this in our own data center. Okay? So here are the definitions, and here are the way to derive the value of CR, either thermodynamically, which is this case, and ends up being about 0.35, or economically, which ends up being also about 0.3, 1.3, and the other one is 0.35, I think. Let's look at our data center now very quickly. We do lots of things with it. So we have the data center. We can feed it with grid electricity. We can shut the turbines completely and just feed it, run it conventionally. Okay? Or we have these micro-turbines. These, the MUT is the micro-turbines. I can feed power to the data center, and I can take the waste heat and either use it for the absorption chiller, that ABC is the absorption chiller, or I can send it to the heater to heat hot water. Okay, so I can send either cooling or heating to the adjacent building. That cooling and heating in the adjacent building would have displaced chilled water obtained from a conventional screw chiller. So we know the performance of that screw chiller, and we know how it varies with the outside temperature. So for every unit of cooling I send to the adjacent building, that displaces the electricity I would have consumed in the absorption in the screw chiller to cool that building. So that's electricity to electricity, so that's not a big deal. I don't have to worry about the CR. But if it's heat, I can do exactly the same thing as I described before. Okay, that building is heated with a boiler. That boiler has an efficiency. It burns natural gas. So I can figure how much natural gas I'm displacing and substitute that factor that expresses the relative cost of electricity and gas in our expression, in our system. So these are the various metrics we have. Forget about this last metric. Okay, it's not important at the present time. Okay? But these are now measurements. I'm going to show you examples of them. We're continuously collecting data. Okay? The blue line is the traditional PUE. Okay? The green line is that one that's called ERE1. ERE1 and PUE will be exactly the same if you're not exporting any energy. there's no energy export, then the two lines will follow one another. And this particular case shows a case in which we were not exporting energy, but if you look at the PUE, it's less than 1.3. That's a very good PUE, given the fact that because of this belts and suspenders and duct tape, we actually did things that end up increasing the energy consumption of our data center a little bit more than what it would be if our CIO was comfortable, or if this technology is proven and we did not have to do all these additional things. Okay, and you see here a bunch of things. You see the ambient temperature is this one here. So this is some sort of a day near the end of the winter. Okay, this is the fraction of the power provided to the data center that's coming from the turbines. So it's not 100K, it's close to 100%, but it's not quite 100%. And then there are sort of pie charts showing the various energy consumers in our data center. So that's the one that ends up being, I think, what does it say here, 1.26 or something, the PUE. This is a hot day, okay? And in Syracuse, we have this last May, end of May, we had very hot days where the temperature hit 95 degrees. Okay, again, you look at the PUE, in this case, it's still a little bit less than 1.3. We attribute this lower PUE to these combination of things. We're getting the cooling for free. I'm not not using any electricity for cooling. I'm using the waste heat from the turbine for this. And in addition to the water-cooled cabinets that we have, that combination and the various energy efficiency factors we took into consideration in the design of that data center. So it gives us, again, a PUE. But in this case, because it was hot, we were able to export some of the cooling to the adjacent building. That's why our ERE1, the one that subtracts the economic worth of the cooling, is actually lower. And you talk about numbers that are more like, they actually hit a number close to 1. Particular case. If I did it the way Green Grid says I should do it, I would have ended up with a number less than 1. Okay? But these numbers have been attenuated to reflect the actual worth of this heat, okay, as we converted it to electricity and found the electric equivalent of it. Well, thank you very much. Okay.